Welcome and hello. This is a video exercise in HY-8, and in this exercise, I've titled this one Case Study Nicaragua, because what happened was one of my viewers wrote in with their own project files and presented them to me and gave me permission to make a quick video, so I'm honored. Thank you to Elias for the information. This video is not my own work. I am simply the messenger and wanted to demonstrate a real-world example of using HY-8 for culvert design, this project specifically in Nicaragua. All right, let's go ahead and get started. What we have is the HY-8 interface on the screen here. I'm going to actually transition over to a PowerPoint slide where I've made a few images as a way of introduction. Then we'll get back to HY-8. What we're seeing here in this map is what I assume is the location of the project in Nicaragua. There are some 27 or 28 different locations along a proposed roadway or some sort of improvement project that needs drainage, hence culverts or bridges of some sort. Now, to keep this video fairly short, we're going to be just focusing on one location. That is going to be this ODT-9 location. And using HMS or some other software for drainage, the hydrograph or all these drainage basins, specifically ODT9, were calculated for the 25-year, the 50-year, and the 100-year return event. So we don't have any actual numbers in these plots right now, but in the next slide, I do have the actual flow rate. The max flow is what this means, I believe. And this is in meters cubed per second. So this is going to be you're going to have to change your HY-8 units to metric. But yeah, anyway, 25-year, 50-year, and 100-year, we're looking at a peak flow that we need to design for at the culvert of 94.5 meter cube per second, 117.4 meter cube per second, and 144. On the next slide, I have some of the design parameters for this specific ODT9 crossing, and they're right here in this table. So this is mostly Spanish, I understand, and I do have it translated to English right here, at least this first column, which is the label, and then the parameter or the value, and then a couple photos. We can look at a few more photos up close towards the end. But basically what we have here is the station number, the geometric roadway elevation, that's going to be the height of the roadway. The existing structure which is in place here is two barrels that are sized 3.5 meters wide by 2 meters high. So what we're going to be doing in this exercise is first modeling the existing structure with those three design flows, and then we're going to evaluate, and if the culverts need to be upsized, we're going to go ahead and run a second simulation with larger culverts or some sort of improvements. The length of the road is 8.7 meters, so looking downstream, that would be left to right. This would be the length of the weir in the case of overtopping. The road width is 4.2 meters, so not a particularly wide road, but that just means the culvert doesn't have to be that long either. Next up, we have start elevation and station of the culvert, the end elevation and station of the culvert. So yeah, just 4.41 meters is the length, and then the slope is about 1%. And finally, here are those peak flows that we're designing for. 94, 117, and 144 meters cubed per second, or CMS. The last design requirement that was mentioned to me is up on the screen here. This is the maximum HW divided by D, which is 1.20. That happens to be a specific standard that's used in Central America. HW is the headwater depth, and then D is the rise of the culvert. The return period that we're really aiming to design for here is the 50-year return period for main roads, which is our 117.4 meters cubed. But we're going to run the analysis with all three of these flows just out of curiosity to see how they compare. All right, well, let's go ahead and get started. I'm going to go back to my HY-8, and we're going to start by adding a project. I'm going to go right click, add a culvert crossing. Now, the name of this culvert crossing, I'm going to say is ODT-9, and then I'm also going to call it existing in the event that we need to create a second crossing with the proposed improvements, the larger culvert, the higher roadway, whatever we decide to do. Okay, let's put in our discharge data. So what I'm going to select here is recurrence interval, and then click on define. We have data for 25, 50, and 100 years. So let me just type that in, 94.5. Oh, I already forgot to change the units. Let me do that before I go any further. I'm just going to click OK. So, okay, looks like that closed the program. One moment. All right, starting over. Well, let's go ahead and change the units first so we don't have to do that again. Right click, adding a crossing. At least we didn't have too much work done. ODT-9 existing. Then I'm going to just click OK now. Click return error. Ignore errors. And let me save this so I don't lose it again. Okay, I'm in my project directory. I'm going to call this exercise2.hy8. Okay, we're saved. We're ready to start making edits. Go right click, culvert crossing data. All right, so back to where were we? The recurrence interval, define. Yeah, this is where we were last time. When I saw CMS on the screen, that's what made me remember, got to do metric 94.5, 117.4, and 144 CMS for those three return periods. I'll click OK. Next is the tailwater data. Now, most of this data wasn't presented to us in the report in the PowerPoint that I provided, but it was in a different page in the report. So let me just type in the numbers here. Tailwater channel type will be rectangular. The bottom width will be 6.96. The channel slope is 1%. Manning's N is 0.025. And then the channel invert elevation is 134.76 meters above mean sea level. All right. The roadway data, we did see some of this data, so we're going to go with the constant roadway elevation. The first roadway section, we'll just keep that at 0 meters. The crest length, we saw that was 8.7 meters. The crest elevation, that's the peak elevation of the roadway, that was 1137. The surface, we're going to go with gravel, and it shouldn't have any overflow anyway, but the top width will be 4.2, so that is the width of the roadway. All right, heading over to the other side here. The culvert name, let's go ahead and name this, how about 2CCR 3.5x2? Simply describing that we're going to have two barrels that are sized 3.5 meter wide by 2 meter high. In fact, let me go ahead and update the barrel number now, which is down here. So I'll change that to a 2. The shape is not circular, but rather concrete box. But I remember reading that circular was all right. We're going to go with concrete box here, though. The span will be 3.5 meters wide, rise 2 meters high, and that's in units of millimeters. So let me not make that mistake. Okay, 3,500 millimeters and 2,000 millimeters. Embedment depth 0, Manning's N 0.012. That's typical of concrete. The inlet configuration is, again, we're just using the default here, square edge, head wall. And inlet depression is going to be no. All right, the last data we need to input is our site data here. This data was all provided, so this shouldn't be too big a deal. Inlet station was 0. We'll just leave it there. Inlet elevation, 1134.80. Outlet station is 4.41. And then the outlet elevation is 1134.76. So here's the slope. It's basically a 1% slope, and that's through the culvert. It's a straight culvert right here, so nothing weird with like tapers or broken backs. All right, let's go ahead and analyze. I'm going to click this Analyze Crossing button. We're going to get some results here. Here is the first list of results under the Display Crossing Summary table. And what we have is the 3 different return periods for the 3 rows that we inputted data for. The roadway elevation is 1137 meters, and it looks like all 3 of these flows produce a headwater elevation that exceeds 1137. In fact, we have 1137 fixed right here, which is right at the overtopping, which corresponds to 32 CMS. But our 3 design flows are all 94, 117, and 144, so way above overtopping, which basically means the existing culverts cannot withstand or even convey the 25-year flows, not even close. So let's look at a few more details on these results and then transition into making some improvements by redesigning the culverts at this same crossing location. All right, for each of these 3 flows, we have the flow through the culvert, and then we have the amount of flow in CMS flowing over the roadway. So the 100-year flow actually has more water flowing over the roadway than through those 2 culverts. All right, I'm going to click on the next radio button down here. This is Culvert Summary Table. And what we have in this table is a lot of the same data for the first 4 or 5 rows. We have inlet and outlet controls, so you can see bold, the larger number between inlet and outlet is actually controlling that headwater, which we can confirm if we click on this Culvert Performance Curve button. The values are pretty close right down here at the 25-year return event, but for 50 and 100, It's definitely outlet controlled. Either way, all these flows are way higher than they are allowed to be for our current culvert. For instance, this HW divided by D quotient cannot exceed 1.2, and we're looking at numbers at 2, 2.29, and 2.61. The flow type right here, 4-FFF, that corresponds to outlet controlled for, I believe, submerged inlet and submerged outlet. If we click this flow types button, we have, got to find it. Okay, it's this one, 15, outlet controlled. It's submerged for the full length. 4 is the flow type. It's in this column, so it's submerged. And then lowercase f means the tailwater is also submerged. Okay, so I'm going to click close there. If you want to take a look at the plot here, we should see it by clicking here. Okay, we have headwater and tailwater. Not sure. Oh, so this is 144. This is the 100-year flow. If I wanted to see the 50-year flow data, I'd have to open up the culvert data. And then I guess I could change this so that the design flow, what was it, 117.4? Okay, so let's type in all three numbers, I suppose, 94.5 and 144. All right, so I'm going to analyze that and then close. Here we go, 117.40 CMS. This is just a visual of the headwater, the tailwater, and of course the culvert is flowing full. From the PDF report that Elias sent me, translated into English, there was a paragraph that concluded what we've already learned from the existing culvert situation and the analysis, and it reads, the results of the profile and cross-section indicate that the water depth exceeded the height of the box type section, even rising above the roadway elevation. Therefore, the structure must be replaced with one that meets the design flow and road design requirements. All right, so what we're going to do in the rest of this exercise is close this data, come up to the crossing data. I'm going to go right click and then duplicate, and then I'm going to rename that crossing. And instead of existing, this is going to be called proposed. And then instead of this particular culvert name, I'm going to rename that as well. This is going to be 3 CCR 5X4. So what that means is we're going to have, well, right now it's just a copy of the 2-barrel 3.5 by 2. But now it's going to be, we're going to change it to make some edits. So it's 3 barrels, 5 meters by 4 meters. Now, thankfully, we don't have to make a ton of changes. Not everything here is going to change. For instance, the discharge data, that's all going to be the same. The tailwater data, just making some checks here. Yeah, that's exactly the same. The roadway data will have a few modifications. For example, the crest length is going to be widened to 15.5 meters. The crest elevation will actually be raised about 2 meters to 1139.05. The surface will still be gravel, and then the top width will still be 4.2. So the roadway width will not change, but it will be raised a couple meters, it looks like. Over on the culvert data side, it's still going to be a concrete box. The size is going to be 5 meters wide by 4 meters tall. We can get away with that extra rise because we rose the roadway elevation right here. Everything else looks good here. I'm just checking with my data. Yep, good. Okay, and the only difference here was it was 0.75 at the end. And oh yeah, the number of barrels, that's 3. Details, right? That's important. Make sure to change the number of barrels to 3 if you're doing this exact same example as me. It's again about 1.1% slope here. All right, so let's go ahead and click the Analyze Crossing and see what sort of results we get this time. All right, so starting off with the first radio button, Crossing Summary Table. Actually, you know what? Let me change the flow back to just those 3 design flows. I'm going to click this Edit Input Data and then change this to Recurrence, Define. Okay, the data has been saved. That's good. I'll click OK and then Analyze Crossing. All right, cool. So now we have our 25, 50, and 100-year flows. Keep in mind the new roadway elevation is 1139, and it looks like all 3 of these flow rates are not overtopping the roadway. And keep in mind, this is the peak flow of the 25, 50, and 100-year storm events. There's 0 roadway discharge, so that makes sense. And yeah, we're looking good so far. Let's check out the culvert summary table right here. We still have an outlet controlled culvert. That's fine. What's important is that HW divided by D quotient right here is less than 1.2. It's actually less than 1 because remember the 50-year storm event is what we're really designing for. It's down to 0.88. The flow type is different, that's for sure. Let's see which one that is. 1-S1T T. So I'm going to click on flow types right here. I believe that's right here, row 3. It's outlet controlled. 1S1T. Okay, thank you, USGS. And the tailwater velocity right here is 5 and 5.5 and 5.8 meters per second. There was some design requirement about no downstream erosion, but I believe this is flowing into a concrete channel anyway, just due to the Manning's N and the other tailwater conditions, like it being rectangular in shape. If we check out the culvert performance curve, yeah, it looks like it's still outlet controlled for all 3 of our data points, all 3 of our flow rates. And if we're curious about what the water surface profile is through the culvert, let's check out the 50-year. So I'm going to click on water surface profiles and then 50-year, and then click on selected water profiles. Okay, here's that plot. What we have is the headwater right here at about 1138.4. The tailwater is right here, right at the water surface. Normal depth, critical depth, and water surface elevation. So that makes sense. When it's outlet controlled, we have subcritical flow. And again, this is 117.4 CMS. It looks like there's about 1 meter of available space in the culvert that the water level can still rise. But we don't have to guess just by looking at the plot here. I can close this. We can click on the water surface profile data. And now here are the actual numbers. So the distance from the inlet goes from 0 up to the total length, which is 4.41 meters. That's the length of the culvert. And we can see the water depth is about 3 meters. Yeah, it looks like it's just above 3 meters, perhaps slightly rising as it flows through the culvert. But remember, the rise in this improved culvert, this proposed culvert, is 4 meters high. So there's still sufficient area for additional flow. If we want to go to our plot right here and then check out the front view, let's see here. I go up to display, view, and then front view. Now I need to specify the actual road stationing for the center of these culverts. So I'm going to click right click, define roadway culvert stations. All right, so between 0 and 15.5 meters, we'll just presume that it's centered. So that would be 7.75. Type that in right here, 7.75. And then the barrel spacing is the spacing between the barrels. So if they're 5 meters wide, we could say it's, I don't know, 5.1 meters. I don't know. Let's see what happens with that. Oh, never mind. I misunderstood that. I'm sorry. Go back to define roadway culvert stations. So let's just go with the 0.1 here, see what that looks like. Okay, I'm pretty sure that's what they were going for. That's what the picture looked like for the existing conditions. Now keep in mind, these culverts are 5 meters wide and 4 meters tall. They look taller than they are wide, but just remember that the stationing is, or the scale is different for the stationing and the elevation. Before we finish, I just wanted to show a few real pictures of the project. So this is the roadway. The culvert would be down here, flowing left to right underneath the roadway. Here's another picture of the culvert. So I'm not sure the direction of flow, but you can see there's really no space between the top of the culvert and the top of the road. I believe this would be the existing conditions. Here's another photo right here. You can see there's quite a bit of vegetation in the existing culvert. You can see it's a rectangular culvert, so it would be 3.5 wide by 2 meters tall, or 2 different culvert barrels. And that tailwater canal, the tailwater data would be rectangular canal. All right, well, that's it for this exercise. Thank you to Elias for providing the project and allowing me to make a presentation. For those of you learning HY-8, I hope you found this exercise helpful. It was a case study in Nicaragua.